All right, so we're back. We're ready to pick up on chapter 9 again and finish up with some application type things, application type situations in quadratic functions and when we need to use the quadratic formula. So the point of today is to be able to use quadratic equations to model some situations and see when we need to use the quadratic formula to help solve. And those applications, there are a lot of applications for quadratics, but one of the most popular ones is the idea of what are called vertical motion models. Vertical motion models is basically something to the effect of if you throw something up in the air and it's going to come back down, and so make a parabola. That kind of thing. Or if something's launched up into the air and comes back down, right, you kind of get the idea that those are going to be parabolas. And so modeled by some quadratic functions, okay? If an object is dropped, so it's not thrown, but it's just released and dropped, then there's not an initial velocity, and so we're going to have one less term than if an object is thrown, right? It'll have an initial velocity. But those are your two models, and they're going to be the same, right? Whether you throw or launch something or drop something, then the models are going to be the same. They're always going to look like this. H equals negative 16t squared plus vt plus s. And that alphabet soup, basically, out of all of that, the H stands for the height at any given time, whether it's the final height or some height after so many seconds. S is the initial height, right? Sometimes it'll be 0. Sometimes you're going to start from the ground. And sometimes you'll have an initial height. T is time in motion, right? How long it's been moving. And V is the initial velocity in feet per second. Now, one thing to pay attention to is if you throw something downward, then V is going to be negative, right? The initial velocity is going to be negative because it's going down instead of up. So we kind of think about these vertical motion models as launching something up into the air. So if you're not launching but you're throwing something down, then the velocity needs to be negative. Okay, let's take a look at how to use these. First situation, a rocket is launched from atop a 71-foot cliff with an initial velocity of 30 feet per second. The height of the rocket after, need some typo there. Wait a minute, what's that saying? The height of the rocket t seconds after launch is given by the equation. Sorry, okay. So here we go. That's our function, right? So the height in terms of t, right? Because obviously the rocket's going to go up and come back down after so much time. So based on the amount of time has gone by, this function will tell us how high the rocket is. How long after the rocket is launched will it hit the ground? So a picture usually helps out a lot here. So we have some cliff here that's 71 feet high, and we're going to launch a rocket off of it. Okay? So this rocket is going to go up, and, well, it's going to do better than that. Here, let's give ourselves some more room. Right? It's going to go up and come back down and hit the ground after so many seconds. We want to know when it hits the ground down here. Well, the model for this situation is given here by this function. H equals negative 16t squared plus 30t plus 71. The question is, how long after the rocket is launched will it hit the ground? Well, if it hits the ground, how high off the ground is it? Right, it's not off the ground at all, so the height would be 0. So we can let the height be 0 and plug in 0 for H. Okay, so that's what we've got to solve, right? We've got to solve for t. How long after the rocket is launched? We've got to come up with what t is. So we need to solve this particular equation. Okay, well, we can certainly go through our process of solving. We could try to graph this, which I don't want to do. We can't use the square root method because we have this b term. We could try to factor it, but we haven't really talked about how to factor when your a is negative. So we're left with quadratic formula. And since t is sitting in place of the x, we're going to let t be x. So our quadratic formula says that t is equal to opposite b plus or minus square root of b squared minus 4ac all over 2a, where a is negative 16, b is 30, c is 71. And so we just plug in and go to work. So negative 30 plus or minus the square root of 900 minus 4 times negative 16 times 71. All over 2 times negative 2 times negative 16. And that's what we got to solve. Okay, so we start simplifying. This is negative 30 plus or minus the square root of 900 plus 4 times 16 times 71 is 4,544 all over negative 32. We're going to go negative 30 plus or minus the square root of 5,444 all over negative 32. And you got to find a way in your calculator to calculate out what negative 30 plus the square root of 5,444 is all over negative 32. And negative 30 minus the square root of 5,444 all over negative 32. Okay, so we type that in, negative 30 plus the square root of 5,444. Divide that by negative 32. And one of the t values is negative 1.37. The other one, so we go negative 30 minus the square root of 5,444 divided by negative 32, and we get 3.24. Okay? Now, can time be negative? And the answer to that is no, obviously. So what we need now is to, well, one thing we need to ignore the negative answer, because t can't be negative. We need to come up with a nice sentence answer here that says that after about 3.24 seconds, the rocket will hit the ground. Okay, make sure you always include that sentence answer. But that's it. We're just solving for t. And t will tell us the time that it takes for it to hit the ground. Because, again, the height is 0. Okay? So there's one use. Could also use this model to figure out the maximum height of the rocket. Again, rocket's going to go up, come back down. The maximum height is going to be right here. We've actually done this before. We were just trying to find the vertex. Right? So the vertex is going to need a t value. Again, it would need to be, you'd need to find x, plug it in to find h, but, sorry, h, plug it in to find y, but x has been replaced by t, and y has been replaced by h. So to find the t coordinate of the vertex, we just do the opposite b over 2a that we did when we were graphing before. Opposite b is going to be negative 30. 2 times a is negative 32. And so about 0.9375 is what we get here. And that's for t. That's time. That's seconds. So what does that mean? It means that after 0.9375 seconds, the rocket has reached its maximum height. So less than 1 second. The question is, what is that height? Well, now that we have t, we can plug that in and go find out what h is. And so now it just becomes a calculation thing. So we're going to square 0.9375 and multiply by negative 16 to get negative 14.0625. Then we're going to add 30 times 0.9375 to get 28.125, and then add 71 to it. We add all of that stuff together, and we get 85.06. So the maximum height of the rocket is about, or was about, 85 feet. Okay? And there you go. And again, we've done this before. We were talking about Pat McAfee kicking a football and some other options as well, some other things as well. Throwing a shot put. Okay, so this should not be brand new, but it's been a little while since we've seen it. Sometimes you're going to have to come up with this function yourself. So you're going to have to remember that the format of this function is h equals negative 16t squared plus vt, where v is the initial velocity, plus s, where s is the initial height. Okay? For example, here, the height of an object thrown upward with the velocity v feet per second is given by that, where t is time measured in seconds. If an object is thrown upward with a velocity of 80 feet per second from ground level, how long will it take to return to ground level? The picture's always nice, and the object's going to start here. It's going to get thrown up and come back down to the ground. So it's a parabola. We need to know when h is 0, right? There's going to be two times when h is 0, one before it's thrown and the other one after it's thrown. Okay? Now we don't have anything in here for v, but we do know that the initial velocity was 80 feet per second, so that needs to go in here for v. Okay? So we start with h equals negative 16t squared, and since it's being thrown up, the velocity is going to be positive. Now, you can look at this. You can certainly use the quadratic formula if you'd like, but what we know is that the height is going to be 0. We want to know when the height of this object is 0, because it means that it's on the ground. And so we need to solve this equation right here for t. And you can definitely use the quadratic formula, but I would recommend you try to factor first. And since we're missing this c term out here, the constant, we can actually factor this using a greatest common factor. These two terms right here, what do they have in common? Well, they're both divisible by 16, and they both have at least one t. So we can divide out a 16t from each term. When you divide negative 16 by positive, when you divide negative 16 by positive 16, you get negative 1. When you divide t squared by t, you get t. When you divide 80 by 16, you get 5. And when you divide t by t, you get 1. And so we're just left with negative t plus 5 times 16t. Now, the zero product property still applies here. If we've got these two terms that we're going to multiply together, and they have to equal 0, that means that one of these terms has to be 0. And we don't care which one, so we can set them both equal to 0. And find out when the t will be 0. We divide by 16, and 1t is going to be 0. Subtract 5, and divide by negative 1, The other t is going to be 5. So what does that tell us? There's two t's. Which one do we use? Well, here's when t is 0 and when t is 5. What does it mean for t to be 0? Well, if t is 0, it means that no time has passed yet. Nothing has happened yet. So t equal to 0 must be right here. Right? Because nothing's happened yet. Then we throw the object and it lands again. And apparently when it lands on the ground again, it's 5 seconds after it's been thrown. So how long will it take to return to ground level? It takes 5 seconds. So good sentence answer, it will take 5 seconds for the object to reach, or for the object to return to ground level. Okay? So here we didn't have to use quadratic formula. We can just factor and solve that way. Okay? Along the same lines, again, what is the maximum height? Okay, well, we have the formula again. We already have the model. We just used it. And again, the initial velocity was 80 feet per second. We want to know what the maximum height is. So we're not going to try to solve this equation like we did in the previous example. We would think about maybe trying to graph it by finding the vertex. Finding the t-coordinate of the vertex by using opposite b over 2a, which is going to be negative 80 over 2 times negative 16, which is negative 32. Right? So 80 divided by 32 means that after 2.5 seconds, the object has reached its maximum height. What is that maximum height? Well, plug it into the function and we'll be able to tell. Right, so we're going to take 2.5 squared times negative 16, which is negative 100, plus 80 times 2.5, and that's 200. Add those together. And the maximum height for that object is going to be 100 feet. So a good sentence answer, the maximum height of the object was 100 feet. And we're good. Okay? Now you may need to fill in more of the formula than even that. For example, consider that a falcon's diving toward a pigeon on the ground. When the falcon is at a height of 100 feet, the pigeon actually sees it. Okay, and the falcon's diving at 220 feet per second. So really, what would be useful for the pigeon is to know how long it has to get out of the way, right? Otherwise, the falcon will scoop him up and eat him. So how long before the falcon gets to the pigeon? Okay. Again, we need, you can use a nice picture here. So there's the falcon. Here's the pigeon, whatever, okay, and he's coming down, right? So he's thrown himself downward, right? We need a quadratic function to model this. Well, we know that from the beginning of the notes here that this basic model is what we want to use, right? So where we're going to fill in everything except for h and t. So v is the initial velocity, and that's at 220 feet per second. And s is the initial height. Now, the falcon didn't start 100 feet off the ground, but that's when the pigeon saw it. So from the time the pigeon saw the falcon, the initial height was 100 feet. So that needs to go in for s. right? And since the pigeon's on the ground, the height of the pigeon's at 0. So we want to know when h is going to be 0. So now we've got ourselves a quadratic equation that we're going to want to solve, right? We could try to factor it, and that's fine. But again, factoring with 16 being negative could be tough. And these numbers are pretty big. So I'm going to do what I've always said not to do, and that's kind of default to the quadratic formula, right? Opposite b plus or minus the square root of b squared minus 4ac all over 2a. Right? Opposite b, b is 220, so we get negative 220 plus or minus the square root of, now we got to take 220 and square it, minus 4 times negative 16 times 100 all over 2 times negative 16. So we get negative 220 plus or minus. Now we're just simplifying. The square root of 48,000. $400 plus 4 times 16 times 100, which is 6,400. All over negative 32. Right, we're going to keep working on simplifying. So t is equal to negative 220 plus or minus the square root of 54,800 all over negative 32. We're going to come over here and keep on simplifying. Any chance the square root of 54,800 is going to be an even number? Of course not. So we need to go negative 220 plus the square root of 54,800 over negative 32. And we need to go negative 220 minus the square root of 54,800 all over negative 32. And see what kind of answers we get. So, negative 220 plus the square root of 54,800 divided by negative 32 gets us negative 0.44. And now go the other way. Negative 220 minus the square root of 54,800 divided by negative 32, which is 14.19. So what do those numbers mean? Well, again, time can't be negative. As much as sometimes we want to go back in time, we can't. And so we can't use this time value. So we're going to use 14.19. And what that means is that from the time the pigeon sees the falcon, it has about 14 seconds to get out of the way. So we can say that it will take the falcon 14 seconds, or about 14 seconds, for the falcon to reach the pigeon. Seems like a lot of time. So the pigeon should be able to get out of the way. Okay? Now, at the same thing. And so there we go. Any issues, questions there? Make sure you come in and see me and we'll work through it. All right? So you got one more here that I'm going to let you work on. You need to come up with the model first, the function first, and then try to find how many seconds will a rocket have an altitude of 90 feet. Think about that. Stop the video, give it your best shot, and then start it back up and see how you did. Okay, sorry, it had to take a second to verify this, but yeah, it looks like we have a situation where negative 65 plus or minus the square root of 4,225 minus 5,760 is negative 1535 all over negative 32. Problem is, well, lost my work above that, but it's okay. We can't have a negative inside the radical, so this is actually no solution, which means the rocket will never reach 90 feet. Okay? I'm not sure if that's a typo or what, but apparently it's never going to reach an altitude of 90 feet. Okay? All right. But anyway, still a pretty good use of filling in the model to create the model function. I just realized that you guys didn't see any of this yet. So let's even back up further. That's what happens when you kind of get messed up by the numbers here. Anyway, the model you should have come up with is this right here. So h equals negative 16t squared plus 65t. Did not have an initial height, so there was not going to be any constant there. We want to know after how many seconds the rocket will have an altitude of 90 feet. That means instead of setting it equal to 0, we need to set it equal to 90, which is what we did, is what I did here. So might have been where you need to change some things, okay? So we want the altitude to be 90. That means h is going to be 90, so we set it equal to 90, and then go through our solving process. Remember that your equation has to be equal to 0, so we subtract 90 from both sides to get this right here. And then we can go start doing quadratic formula. The problem is you end up with a negative inside your radical, and you can't have that. So it's no solution, and so the rocket apparently will never reach 90 feet. Okay, but still need to be able to fill in with the information given. If there are any questions about that, make sure you come see me. Okay, homework's out there in Canvas. We'll see you next time.